So assertion reason question. If an object is submerged in fluid at rest, the fluid exerts a force on its surface. Reason, the force exerted by the fluid at rest has to be parallel to the surface in contact with it. This is a correct option.
I think option C, ma'am.
Option C. What you're thinking is correct. Assertion is correct, but reason is incorrect. Okay. Then now liquid is at rest. Liquid in a container. Liquid is at rest. And an object is here. So the force exerted by the liquid should be normal. It should be like this. It should be like this. It should be like this. It cannot be any other angle. If the force is inclined like this, then it will have component, isn't it? It will have a component. The force. So now it is, the condition is the liquid is at rest. It is not moving. It is in equilibrium. So if any force acting in this direction will have two components. Vertical and horizontal. This horizontal component, what is the effect of this horizontal component? What is the effect of this horizontal component?
Pressure exerted at the...
It will make the object to move, isn't it?
Yes,
Can the object move? Can the object move? Here it is in equilibrium. If an object is submerged in a fluid at rest, fluid is at rest. But fluid is exerting force. So the force should not make the object to move. So what should be the direction of the force? What is the direction of the force? It should be perpendicular to the surface at every point. So only perpendicular forces will not have component along horizontal direction. Is it clear? Correct? So if you consider like this, mathematically also we can prove. So any force exerted by the liquid at rest on any object should be perpendicular to the surface at every point. So if you consider the force, if I say that force is acting like this, so this force will have two components. It makes an angle theta with a horizontal, F cos theta and F sin theta. Isn't it? There is no flow. Liquid is not flowing. So F cos theta is 0. There is no flow along the horizontal surface. So F cos theta is 0. So what is the only F is there? Force is exerted. Liquid is exerting force. So what is the condition here? We are getting a condition theta is 90. That means whatever force acting should be perpendicular to the surface. The liquid exert force. The force exerted by the liquid must be normal to the surface. If the liquid is at rest, the force exerted by the liquid on any object or any part of the liquid, other part of the liquid. This can be other part of the liquid too. Need not be any external object. So liquid, the force exerted by liquid is always normal to the surface. Okay. So that normal force only we call it as thrust. Admit Varadha miss. I'm admitting. Now I'm admitting. Yeah. Admitting. Okay. So now, here, so now the force exerted, we are going to study about what is the nature of the force or pressure. Pressure exerted by liquid. If the fluid is at rest, the pressure in a fluid at rest is same at all points which are at the same height. This is Pascal's law. How are you going to prove it? Pressure in a fluid at rest is same at all points which are at the same height. So if you consider...
Ma'am, we can use that bottle experiment where we make a hole at the same height.
Yes. You can actually do this experiment. This is what you're telling, isn't it?
You just showed it in the previous slide.
No, that's, I'll come to that. I'll come to that. You can show by activities. You take a rubber ball and fill it with, make a small hole, fill it with water and make holes here. And if you press the rubber ball, the water will, at one point, if you are applying pressure now, the water will come out in all direction with the same pressure. This you must have, many of us would have played with a ball filled with water, poking holes on the ball. That's okay. So now this is the law which involves transmission of pressure. if I am not transmitting pressure, okay. So in the static situation, I want to prove pressure at A is same as pressure at B. How do I prove that? Pressure at A is same as pressure at B. I assume that the point A and B are very close to each other. The point A and B are very close to each other. So if I assume that it is in equilibrium, okay. So you consider container. So now I am considering a cylindrical surface. This is also liquid surface only. It is in equilibrium, so it is understood that on the curved surface, the force exerted should be same. And here, if you consider this as F1 into A, and this side, the force is F2A. It's an imaginary cylindrical surface. And still, so the net force on the cylinder is 0. So F1A must be equal to F2A because this net force must be 0. Exactly in the, you know that the forces act exactly in the opposite direction. Sorry, I think I'm going wrong page. It is P1A, P1A, P2A. The force is, here it is F1, it is F2. So F1 must be equal to F2 because the liquid is at rest. So P1A must be equal to P2A. So P1 is equal to P2. This is a very simple way you can prove Pascal's law. If the liquid, if you consider these 2 points, A and B to be at the same height, I don't see, they are at the different height, but I neglect the height. They are very close. The depth from the bottom is same. They are at the same. As I'm assuming that the depth from the bottom, depth of A and depth of B is same for the points A and B. Okay, if I neglect the depth, if I consider A, this is a very small cylinder, and A and B, I assume that they are at the same depth. If you neglect the depth, if you have neglect the effect of gravity, in the absence of gravity, pressure at A is same as pressure at B. But if you consider the point, the upper surface and lower surface, they are at different height, then Pascal's law to be modified. So we know that, isn't it? And this is a NCERT derivation. I think we follow this and we prove that pressure here for this surface and pressure on this surface and pressure on the lower surface, P1 is equal to P2 is equal to P3. We prove that. I'm not going to do the proof now. Now, variation of pressure with depth, you know, consider a liquid in a container. You teach that, isn't it? We have to prove that there is a pressure difference, and pressure difference depends on what? Am I correct? So what are the forces acting? It is in equilibrium. No, you have to equate the total force to 0, isn't it? Why? Many forces are acting. F1 is the force exerted on the upper surface A. F2 is the force exerted at the lower surface. And if you consider a liquid cylinder here, the weight of the liquid cylinder act in the downward direction. So these two forces act in the downward direction. Upper force F1, upper force exerted by upper part of the liquid, and the weight of the liquid, it should be equal to the force exerted by this part of the liquid on the surface too. So you add all the forces, F1 plus mg minus F2 should be like this, because F2 is acting in the upward direction. Minus F2 must be equal to 0. So F2 minus F1 is mg. So F2 is P1, P2A. If I consider P2 to be the pressure applied on the phase 2, P2 minus P1 into A is equal to mg. F is equal to P into A, because we already defined. So students should be aware of the definition. You should have taught them what is pressure, thrust per unit area. We always, pressure is normal force per unit area. So pressure difference between any 2 points, if effect of gravity is not neglected, it is rho hg. Okay, so pressure difference between any 2 points of a liquid depends on what? Depends on what factor mainly? What factor?
Height, ma'am.
Height of the liquid column.
Height of the
Density.
liquid column. You can do this activity. I think many of you would have done this
Yes,
activity.
ma'am. Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes,
So now
ma'am.
where
We
is the pressure
demonstrated.
more? Which point pressure is more?
Depth,
Uppermost
ma'am.
point or lowermost point?
Depth.
Lowermost.
Lower
point.
depth.
Lower.
The depth is more. The depth is more. The height or depth is more. This is at a so it is this spout. We can say the spout is at a greater depth. So now the water gushes out with a greater force. High pressure jet, and the uppermost point, that spout, no, the spout is, the depth is less, the depth of water above it, above the spout, less amount of water, so less pressure. So pressure depends on height. Okay, so are we ready to answer this question? Liquid pressure depends on, what is the correct answer?
Height of the liquid column.
Height of the liquid
column.
does not depend on, very good. It doesn't depend on direction. Why? Just now we proved, no? Pressure applied.
Pressure is a scalar quantity.
Yeah, it's same at all directions. Does it depend on the shape? Area of the liquid surface? This is called what? Hydrostatic paradox, isn't it?
Yes,
so the volume of liquid in these, they're all connected. They're all connected. Okay. So the different amount of liquid occupying different limbs, the height is the same. The height is the same. So that's what we proved, isn't it? Pressure difference between any two point depends only on H. Density of all the liquid is the same, H rho G. So the liquid pressure is the same at the bottom. At the bottom, the fluid pressure is same at all points which are at the same depth. I think, can you mute? I think Javed sir, can you mute? Yes. Is it clear? This is the hydrostatic paradox. See, the volume of this container is more, shape is different, shapes are different, volume different, area different. Irrespective of that, the pressure, so they're all at the same depth. Okay. So it depends, the pressure difference between any 2 points depend only on the height. This height will be the same. This is slanting here, even though this is little inclined, the pressure difference between the topmost point and the bottommost point depend only on the height. So the fluid pressure is the same at all points at the same depth. If the points are at the same depth, okay, same depth or same height, they have this much height of liquid column above them, those points will be at the same pressure. Okay, so now let us do one numerical. Okay, so don't see the answer. Determine the height. So based on Pascal's law, we are going to solve this. Determine the height H of oil in the U-tube as shown. All the other details are given. There is a oil here, there is a liquid here. Density of oil is given, density of liquid is given, density of mercury is given. So how will you do this problem? It is an equilibrium. It's an equilibrium. So what you should do? So I'm going to apply the principle that the pressure at 2 points, if you consider the point here and the point here, what is the relation between the pressure between these 2 points? Suppose if I take this as say F, they are at the same depth, isn't it? So pressure at F is same as pressure at C because the height of the liquid column is same, isn't it? AF is equal to CD because pressure at a point depends only on the height of the column. So if you consider, suppose if you move from here, okay, the pressure here will be same as pressure here. Pressure here same as pressure here. Okay, if you consider point 1 and 2, the pressure will be the same. 3 and 4, pressure will be the same. So pressure at F is equal.
Just a doubt.
Yes.
Ma'am, at the point F, there is a little bit of oil also, which mercury also, which is exerting pressure. Won't that affect, ma'am?
It won't affect because as you move from down, move from this point, pressure at 1 and 2 will be the same. Pressure at 3 and 4 is the same. Pressure at F and C will be the same. Okay, they are at the same depth here. Okay, from here they are same. and this point. This is also H, this is also H. So these 2 points will be at the same pressure. Maybe above the point F, there are 2 different liquids, and above C, there is only one type of liquid. Irrespective of that, you should come from the bottom. As you move up, as you move up from the bottom, C and F will be at the same height. So the pressure at F is same as pressure at C. Okay. So now if you consider this, if this is 20 centimeter, this is H. Okay, this is H. This will be 20 minus H. This only you have to find out. Okay. So in equilibrium state, the pressure of liquid at the same level must be equal. Okay. So pressure due to H centimeter of oil and pressure due to 20 minus H. This is H centimeter oil. This is 20 minus H centimeter of what? 20 minus H centimeter of
Mercury.
Mercury is equal to pressure due to 20 centimeter of liquid. So, you know that pressure is given by the formula H rho G. Okay. So, H into the density is 0.9. H rho G plus 20 minus H into 13.6 the density of mercury into G, that is equal to pressure due to 20 centimeter of liquid column, 20 into 1.6 into G. So if you calculate, if you simplify, you are getting it as H as 18.9. So this one H 18.9 20 centimeters. So the length or the height of the oil is more. Actually, it is only 1.1. Why do you think so? The length of the mercury, no, this one. H you are getting it as 18.9. So the level of mercury height difference between C and this height of the mercury column is very less. It is only 1.1 centimeter, isn't it? I think I'm answering to Aparna.
Yes, ma'am. I understand.
Okay. Because the H rho G, see here, actually it is like this. H1 rho 1 G plus H2 rho 2 G is equal to some liquid, H of liquid into rho of liquid into G. That is the formula we are using. Okay. So greater the density of the thing, lesser will be the height in order to give the same pressure. Okay, the pressure depends also on the density of the liquid. Okay, yes. It's an interesting problem. You can expect many problem based on YouTube in competitive examination. Okay. Now here, so far we these Pascal law is for a static liquid in equilibrium. Now suppose if you are increasing pressure at one point, actually if I am increasing pressure, I am using a piston, I am increasing the pressure. So the pressure, increased pressure at one point, okay, when a change in pressure, when I changing pressure at one point, the change in pressure cannot remain stagnant at that point. It is transmitted equally in all directions. Okay, this is another form of Pascal law. So any change in pressure is transmitted undiminished. So based on that only we are going to see many devices, no? What are the devices? What are the devices we are going to see? Any clue? Pascal's law, famous devices. So you can ask the children when you go to repair shop or workstation, car repair station. They see this, isn't it? It's a familiar.
Hydraulic lift, ma'am. Hydraulic lift.
Huh?
Hydraulic lift, ma'am.
Hydraulic lift. This
hydraulic
children would be very, very familiar because when they go to workshop, no, car workshop, they give for that, this they would have seen. So how is that the car has been raised to a certain height? So hydraulic lift, you start explaining about hydraulic lift after telling about this. Okay, so let them visualize because the diagram, no, whatever diagram they are seeing, no, whatever you are drawing, that they won't visualize in practical situation. Okay, all will be hidden here. Only this piston will be seen in the workshop, isn't it? So now you know that you know how to explain this hydraulic. This is hydraulic lift. Hydraulic lift. It is based on Pascal's law of transmission of pressure. So you're applying a small force. So you know what is the equation for this? Pressure at the smaller piston, same as pressure at the larger piston. So when you apply force here, the pressure is transmitted through the fluid. So you have a hydraulic fluid here that only transmit the pressure. So you can get F2 will be, F2 is equal to F1 into A2 by A1. So if I increase A2, if A2 is greater than A1, F2 will be greater than F1. Okay. So I can get a larger force, but I don't, this also you should explain. I want you to take this assignment. Force is enlarged. Do I violate the principle of conservation of energy, or how I account conservation of energy? I'm applying a small force, I'm getting a larger force. How to account law of conservation of energy? This one I would like you to take as an assignment question. Okay. How to account for law of conservation of energy? I'm applying a smaller force, I'm getting a magnified force. Yes or no? Correct?
Yes, ma'am.
Yes.
Yes.
So how to account for, how do you account for law of conservation of energy? We say that energy, whatever energy applied, work done here must be equal to work done here. Work done at the other end, work or energy derived at the other end. Okay. So can you find out what is F here? So you have a syringe and you have the, what is the force applied on the stopper? There is a smaller area here. So this is P1 now. This must be equal to P2. So can you calculate quickly and tell me? F by F1 by A1 is equal to F2 by 8. I want the answer now. 60 by 3.
10 Newton.
5 in 10 power minus 1. Same unit, centimeter square. So I can take this. So what is F? 30 by, somebody told me 10. Good. 10 Newton. Good. It's 10 Newton. Is it 10?
Yes, ma'am.
Correct.
Yes, ma'am.
Yes. So we can also do some, see, we can construct a hydraulic lift, isn't it? Using syringes. How many of your students tried using syringes hydraulic lift?
Student.
Using
Yes,
syringes, you can demonstrate projectile motion. We already discussed that. Your students have tried. Is that?
Yes, ma'am. Yes, ma'am.
Gracie, ma'am.
Yes, ma'am. I saw
Very
that.
good. Very good. Very good.
Hydraulic lift.
Yes, very good. Hydraulic lift. You can try this. Okay. Now hydraulic brake system. Hydraulic brake system. It is also based on Pascal's. Now you know that when you are always when I teach that, I ask the students to observe the driver. So the driver of a bus or car driver, your parents, how many pedals are there? There is a brake pedal, there is an accelerator, there is a clutch. So what happens when brake pedal is pressed? There is a master cylinder, the liquid in the master cylinder is pushed into wheel cylinder. So the pressure applied at the master cylinder is same. It is equally transmitted to the wheel cylinder, and the wheel cylinder pushes the brake shoes, and the brake shoe touches the inner rim of the wheel. So the wheels come to a stop. So immediately the children will ask, or you can ask the children, how many, do all the wheels have this arrangement? Do all the wheels of the vehicle? There are 4 wheels now? Yes.
Yes.
You should make them understand that. And suppose if you're giving the car for the service, and if you get the worn out brake shoes, show all this item to the children so that they will have the view of what they see in the diagram. What is the structure actually is different, isn't it? So this fluid dynamics is completely a topic of engineering. So many of them would be interested to take mechanical engineering. They'll be really thrilled when you show them the real device, and you are, if possible, show these pictures. During online classes, we show all this picture. This doesn't mean that now it may not be possible. At least in few cases, really, if you can get a brake shoe, please show it. Because see here, The way we draw the diagram, we draw the diagram at the center. Is it located at the center? This part. No, there are many other intricate parts here. How the transmission, how it is transmitted to each wheel. So there is a axle, a rod here, which is connecting these two wheels. All this, no, this, let you go beyond the diagram given in the text. And teacher, tell me whether these are all very essential for you to do. At least give them the links, let them see the images. Do you think is it all necessary?
Yes,
I think it will help them to connect to real life, like why
it is. Yeah, we have to connect all this to real life. Then only they will get interest. So they may have certain interest in certain type of engineering, or they may not know. They may not know when they take engineering courses what all they will learn. If you tell them these are the things you are going to learn in detail, they will get some interest to do mechanical engineering or electrical engineering or architecture, whatever it is. Let us ignite some interest in the children. You know, let us not stop what is given in the book. Okay. So this is a device. They sell this apparatus. Actually, I saw in the net. We can also buy like instruments, or we can try to do this. I think you can easily do this, isn't it? And we can easily demonstrate this. Okay, next is viscosity. So what is viscosity? What is viscosity? So immediately viscous means we think about honey, isn't it? Because honey, the flow of honey is low compared to flow of water. Okay, it is immediately when you teach viscosity, what do you tell the children? When you introduce a topic, viscosity, how do you introduce a topic to the children?
If you pour the water and oil on the floor, how it will move?
It will move. Whereas when you can't afford to pour honey, isn't it? And you
by
can
touching,
ask us
by,
to
by touching that water in between the fingers and oil and honey, that
yes,
difference they may feel. Now that is a thickness of fluids, that water and oil, honey, that they may feel easily.
And what I do, I take a beaker and then a stirrer. Okay, and I stir the water. When you stir the water and leave it, will the water continue to? So it will move in spiral path, isn't it? When you stir the water will move in as long as you are stirring, the water will move in a coaxial cylinder, isn't it? The water will move in a coaxial cylinder. But as soon as you stop the stirrer, movement of the stirrer, the liquid will come to rest, isn't it? The water will come to rest. Even if the water less viscous, it will come to rest. I'll you ask the children, why is that it is coming to rest? If the liquid is moving, it should continue to move, no? According to Newton's first law, the liquid come to rest, isn't it? Why does the liquid come to rest?
internal resistance.
Because it is feeling the resistance. There is some resistance to the fluid flow. That's why it's coming to rest. Okay. So there is the internal resistance to the fluid flow. And different fluid exhibit different, or they experience different amount of resistance. The amount of resistance experienced by different liquid depends on the characteristic of the liquid. So the honey experience greater resistive force to the flow compared to water. If you take, so we try to explain the cause for viscous force. So we compare it with the frictional force, isn't it? Friction is, in the case of solid, opposing force is friction, is it not?
நிறைய பேரண்ட்ஸ் இத பாருங்க, இங்க பாருங்க, அவங்க பாட்டி நம்மளோட இதுல காரிடார்லாம் நடந்துகிட்டே போறாங்க. இல்ல யாரும் அப்படி எல்லாம் நடக்கூடாது, அங்கெல்லாம் இருக்கக்கூடாது, எல்லாரையும் கீழே இறங்க சொல்லுங்க.
பசங்க
அங்க இருக்கு, கேம்ல இருக்குன்னா.
So if a liquid is moving in a tube, or suppose you are applying if you assume that liquid is restricted between two parallel plates, and if you are giving a velocity v, this velocity v, the layer which is close to this top plate. So you take two plates here. Actually, you consider two plates, two parallel plates like this. And then, or you can assume a tank. The bottom is fixed here. Assume a tank here. This one is open. The open tank, and then take a slab and move the uppermost layer of the tank, completely filled with water, and you are moving the uppermost layer of the tank. So that will have maximum velocity, isn't it? This bottom of the tank, the layer close to the bottom of the tank is at rest, is it not? So now if you consider the velocity of different layers, which layer will have maximum velocity? The topmost layer, no? I am pushing the topmost layer with a, let's say, rectangular sheet. So the topmost layer will have the greatest velocity, and the layer which is in contact with the bottom layer is at rest. So the velocity go on increases here. So this is called the velocity profile. If you consider water flowing in a tube, pipe, water flowing in a pipe, and this is the axis of the pipe. Water is flowing, or any fluid is flowing. Which layer do you think will have the maximum velocity? The layer at the center, or layer in contact with the walls of the vessel? Which layer will have maximum velocity? Water is flowing through a pipe, let us say. Water is flowing through a pipe.
The center, the axis.
Center layer. Because the layer in contact with the surface of the tube, in contact with the fluid, contact with the tube is at rest, isn't it? The tube is at rest. So the layer, the fluid layer in contact with the surface which is at rest, the velocity will be 0. That's why when the water flow through a pipe, after a long time, you know that there are salt deposition will be there on the inner surface of the pipe, isn't it? Inner surface of the pipe. If you take if you are replacing a pipe because it is worn out, or something has gone wrong with the pipe, there are holes. You just observe the inner section of the pipe. In the inner section, lot of salt will be deposited, isn't it? Lot of dirt, salt. Why? Because the water in contact with the wall is at rest. So the salt get deposited there because it is in contact with the walls of the pipe. Whereas along the axis, the velocity is maximum. So here you can, the arrows, the length of the arrow indicate the velocity. So as you move from the axis to the wall, the velocity go on, decreases. Okay. So with this picture, how do you tell that the flow of liquid, the liquid experience resistance? How do you explain that? How do you explain that? So now I've drawn a velocity profile, the velocity, different layers. Actually, this is in the case of this is free surface. The free surface, water flowing on a river. So free surface has a maximum velocity. And as you go to the bottom surface, velocity V is 0. So now these layers are not separate, no, they are mixing. So each layer is in contact with the neighboring layer. If you consider this as V, the topmost layer is V plus dV. This will have a lesser velocity by dV. So now, if I name this as ABC, if you consider this layer B, so the B is in contact with C. This B layer will be accelerated because of the C layer, and it will be decelerated because of A layer, correct? Because this B layer is in contact with C and A. Okay? Am I correct? Do you agree or not?
Yes.
Yes. So, is it allowed to move with its own velocity? Is it allowed to move with the velocity V? No. Its motion is opposed. Okay. So, there is a force because there is a tendency for the neighboring layer to influence it. So the motion of B is opposite. It experiences an opposing force. It experiences opposite force. That force only call it as viscous force. So the viscous force destroy the relative motion between different layers. Each layer is not allowed to move with a definite velocity. Each layer has each layer experience an opposing force. It is not allowed. It has no independence to have some velocity, its own velocity. Okay. So the neighboring layer tend to influence the motion of a particular layer. So this viscous force, that is only viscous force. So this viscous force, according to experiments, it is proportional to area of the surface, and it is proportional to the velocity. What is that called? There is a velocity difference, no? With change in velocity with respect to distance. What do you call this?
Velocity gradient.
Very good.
Gradient.
So F is equal to minus. Why minus sign?
It is a retarding
Force or opposing force. So viscous force. Viscous force is the opposing force which comes into play to retard the relative motion between the different layers. So the eta is coefficient of viscosity. You define that. You can always define coefficient of viscosity as tangential force. You should understand that it's a tangential force. Just like frictional force is tangential force, isn't it? It opposes the frictional force, opposes relative motion. Suppose you have a road here and a car is flying. The frictional force always acts tangential to the surface. Contact force, it's a contact force. Similarly, this viscous force destroys the relative motion between different layers. Okay, so eta is coefficient of viscosity. It's a tangential force acting per unit area of cross section of layers, maintaining unit velocity gradient between the adjacent layers. Okay, let us learn about importance, a very interesting session, importance of viscosity. So why this toothpaste is given here? See, the flow of liquid is opposed, isn't it? Suppose if you are pressing very hard, and you can also explain Pascal law of transmission of pressure using toothpaste, isn't it? You are applying pressure at one point and it is transmitted at the other end. Okay. If the toothpaste material is very thick, if you apply, you have to apply a larger force in order the toothpaste comes out, isn't it? So optimum, and if it is very thin, it will flow and entire tube will get emptied soon. So correct viscosity, the fluid viscosity to be optimum, in order that with the minimum force, you have to get the toothpaste and it should not overflow. Okay. And in machinery, how viscosity of, we use lubricant to, what is the function of lubricant? Lubricants. What are lubricants? You have to tell all these teachers. Reduce the friction
between two moving parts.
Between two moving parts. Okay. So now this viscosity, do you use the same viscous liquid during winter and summer? So whatever lubricant you are using in summer, can I use it in winter or vice versa? Or should I change the lubricant, type of lubricant? Think about it.
I think we should change because
I want you to answer this question. This question. What is the answer for this question? Hot syrup flow faster. Isn't it? Hot syrup flow faster. So viscosity is a function of temperature. As temperature increases, what will happen to viscosity? Viscosity increases or decreases?
Viscosity
decreases. That is the reason flow becomes better. So when the hot syrup So syrup, when the syrup is hot, it flows better. When the syrup become cold, now what will happen? Viscosity become larger. Okay, viscosity become high and it will not flow. It will stand at one point. Okay, the same thing applies here. Okay, so the viscosity of any lubricant inside a piece of machinery. Okay, so the see, between two moving parts you apply lubricant so that they don't rub each other. Okay, they don't rub each other. The moving parts don't get eroded due to actual rubbing. But during summer, when you use a lubricant, high viscosity liquid should be used because they should not flow. When they see, when during summertime, if you use a low viscosity liquid, they will flow away. During as temperature increases, viscosity decreases, and they will flow away from the moving part, isn't it? They will flow. They flow off. They will flow off the machine parts. So machine parts will directly come in contact, and wear and tear will happen. Whereas during winter, what happens is whatever lubricant you are using, it becomes thickened. Viscosity increases, and the moving parts will get what? What will happen to the moving parts? Will they not get jammed? Yes or no? They will get jammed because of high viscosity. So you have to change the type of lubricant. You have to change the type of lubricant according to whether it is summer or winter. Okay. So viscosity, variation of viscosity should be kept in mind. Yeah, very interesting. Now, if you are drinking a thick shake, the shopkeeper will give you a straw. And if you are drinking a juice or water, are the straws similar or different? Straws for a thick shake and a juice. What type of a straw would you use for a thick shake? Will you use a thin straw or thick straw? Thick straw. Thick straw, right? Thick straw with a larger hole, no? Because viscosity of thick shake is more. In order to force the shake through the straw, you need a larger hole. Whereas for a juice or water, thinner straw is more than enough, isn't it? And even in order to pump oil or liquid, you have to design, knowing the viscosity, knowing the value of viscosity of liquid which is to be pumped is very important in order to decide what type of pump is required in order to pump up, say if you are pumping say raw petroleum, okay, petroleum well, you need to pump the oil out. So viscosity of oil is very important. Knowing the knowledge of viscosity of oil is very important for selecting the correct pump, and the diameter of the hose is also very important. Diameter of the hose. You can't use a thin hose in order to pump a heavy viscous liquid. Okay. So this is little interesting. You can talk about thick shake and juice. Students will be really motivated, isn't it? Yes or no?
Yes, ma'am.
Yes,
Do you
ma'am.
tell all this? Honey will not flow at 4 degrees, but flow easily at 30 degrees. Honey flow will stop at 4 degrees. Why? Flow of honey will stop at 4 degrees.
Because viscosity increases and
because
doesn't allow
viscosity will be very high at low temperature. At 4 degrees, it will stop to flow. And we move on from viscosity to terminal velocity. So what is that idea of terminal velocity? So why should we learn about terminal velocity? So far, we studied about the flow of liquid through a pipe, isn't it? Flow of liquid through a pipe, or through a free flow of liquid in a river. So in terminal, what concept we teach in terminal velocity? Tell me, what is the terminal velocity?
It's a constant velocity, ma'am. It's a
constant velocity acquired by a body when a body flow through a viscous medium.
Yes,
viscous medium. Do you demonstrate terminal velocity in your school?
Yes, ma'am.
Yes, we demonstrate. We take a pure end and we take the
doing
ball
experiment.
bearings. We are doing, you are doing experiment.
For 11th standard.
Yes. This experiment, correct?
Yes, ma'am.
What a similar experiment you do? Take a tall jar. We'll come to that. And what I want to ask you is that, so you know, you all teach the forces acting on a small spherical ball, and we discuss about the forces acting on it, isn't it? What are the forces acting on it? You know, weight, then buoyancy. You know that buoyancy is not there. Do you teach in 11th standard upthrust? Upthrust concept you teach? Yes, you teach, isn't it?
Archimedes principle.
Archimedes principle. Already they are learning in 9th standard. So you have to again teach them, because unless they know about the terminal velocity, Archimedes principle, they cannot derive this terminal velocity. This concept is very, very important. So when a solid, this is a solid, isn't it? Solid, a very small spherical body. This Stokes law, no? We derive Stokes law. What is Stokes law? From Stokes law, we derive the viscous force, isn't it? How do we derive it? What method do you employ? What method? Dimensional analysis, isn't it? Correct? Using dimension, we assume that the viscous force is proportional to coefficient of, depends on, this viscous force depends on viscosity, and R is the diameter, radius of the small spherical ball. This is applicable. The Stokes law is applicable to a small spherical body falling through a viscous medium and velocity. So viscous force, and then solving it, we get the viscous force to be 6 pi eta RV. R is a radius, V is a velocity. So you know that this viscous force increases with velocity, isn't it? This viscous force increases with velocity. So when a small spherical body is falling through the viscous medium, the weight, you know, you have to write all the steps. W is equal to mg, and m is equal to volume into density. Volume of the spherical ball is 4 by 3 pi r cube rho g. So this is the weight, and it displaces equal volume of fluid. So the buoyant force is weight of the fluid displaced, which is 4 by 3 pi r cube sigma g. And one more force which is opposing. Why do you think the motion of the ball is opposed? Suppose if the child asks, it is falling under gravity. Why it is experiencing? I agree the weight of the ball is this much and buoyant force is this. Buoyancy or upthrust is this. What is the reason for this? I know viscosity opposes the relative motion between different layers. But now I'm telling this ball is experiencing, a small spherical ball is experiencing viscous force. Why is that?
Change in pressure. Change in pressure, ma'am.
Why change in pressure here? The ball is only falling, no?
But at the height of the depth matters, ma'am.
More than that, is the ball falling with the same velocity as the ball is falling? As the ball is falling, no? Does it not drag the liquid along with that? Does it drag the liquid along with that? Do you think that liquid is at rest? It is dragging. No. So different layers of the liquid acquire different velocity. Correct?
Yes, ma'am. Yes.
Yes, sir. So here it is V1 now. And when the ball is coming here, the velocity of the layer of liquid adjacent to the ball, that instantaneous position, no? The velocity go on changes, correct?
Yes, ma'am.
Correct? So if you compare the velocity here, V1, V2, V3, V4, the velocity of different layers go on increases as the ball is falling. Yes?
No, ma'am.
Why not? See here the velocity, see as the ball is accelerated, it is an accelerated body, no? Accelerated
No.
motion. So
But
V1.
up to that some height only, that velocity will increase.
Yes, yes. Correct. Correct. You are correct. You are correct.
Yes.
You are correct. But I am talking about if you neglect the other force, if you consider only the ball falling with increasing velocity, V1, V2, V3, the adjacent layers will acquire larger and larger velocity, isn't it?
Yes, ma'am. Yes, ma'am.
Yes. So what happens is, if you take this V2 layer, no? V2 layer, this ball will be under the influence of two velocities. Upward velocity will be low, lower velocity will be high. Am I correct?
Yes.
So now, this ball is in contact with the layer. Okay, the contact with the different layers which are under different velocity. So what happens? It experiences resistance to the fall. It is not allowed to fall with G. Ball in air. When the ball is falling in air, its value is G. So when a ball is falling through a viscous medium, because it drags the layer of liquid along with that. As the ball is falling, it also drags the liquid layer along with that. And the different layers are set into motion. Every layer will try to influence the motion of the neighboring layer. In this process, the spherical ball is not allowed to fall. Its acceleration gets reduced. It experiences retarding force. That is only viscous force. That is only viscous force that we derive from Stokes' law. Okay. So whatever we did know, F is equal to minus eta A dV by dx. This is a viscous force which comes into play when the liquid is flowing through a pipe or when a liquid is flowing through a horizontal surface. This viscous force is opposing force experienced by a small spherical body when it is falling through a viscous medium, because different layers in contact with the falling sphere acquire different velocity. These layers of liquid oppose the acceleration of the solid sphere. Is it clear? Of course, this viscous force increase with the velocity. As Sir said, at one stage, the total upward force, the buoyancy and the viscous force becomes equal to the weight. At this stage, now see here, the ball is almost, it has acquired velocity, the terminal velocity. That's what we call it as a terminal velocity. I think the third cylinder is filled with a highly viscous liquid, and the first cylinder is filled with the lowest viscous liquid, maybe water. Okay, the terminal velocity formula we derive, isn't it? Are you agreeing with my explanation?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Okay, I don't need to derive this, no need to derive. No need. So the terminal velocity is inversely proportional to eta. We get this derivation, isn't it? So 2 by 9, r square is the radius of the sphere, rho is the density of the solid, density of the liquid. Okay, eta. So if eta is more, terminal velocity will be small. So terminal velocity is the maximum constant velocity acquired by a small spherical body when it falls through a viscous medium. Okay, so now if the density of the solid is greater than density of the liquid medium through which it falls, this terminal velocity will be positive. The ball will move down. It can happen otherwise also. No, if the density of the spherical body, sphere, is less than density of the liquid, what will happen?
It will float,
This rho
ma'am.
is less. Huh?
It will float, ma'am. Flotation of the.
It will flow up. Have you observed this? A small spherical body moving up. Where?
Bubbles.
Bubble. When you are inverting a water can, bubble topper,
Yes,
no?
ma'am.
When you are inverting a water air bubble escape, no? How do they escape? They move in the upward direction, no? In that water can. So you are inverting a water can here. So when you are inverting a water can, water is getting filled here and air bubble escape, no? How do they escape? They move up, isn't it? Air bubble move up, is it not? Have you observed? Every day we invert and we use a water can and then we invert the top motion, the can over the vessel. So when we are inverting, water bubble escape, isn't it? Air
Yes,
escape and
yes,
water
yes.
enter. Air escape. So the air escape in the form of bubble and the bubble move in the upward direction. Why they move in the upward direction? They also grow in size. They grow in size. Have you observed? The water bubble will escape. Sorry, the air bubble will escape and they will grow in size. The air bubble will grow in size. And this is this also one question for you. You have to find out why. You just observe this, what is happening.
Density decreases and due to the density increases, pressure decreasing and moving upward direction.
Yes, pressure at the bottom is more. Isn't
more,
it?
yes,
Because
pressure at the bottom more.
So pressure, it is compressed. The air bubble is compressed. As it rises, the depth decreases. Depth decreases, isn't it? The air bubble at the top is under a height of water column of less depth. So the pressure above, pressure here is less. So pressure inside is more. So it expands. Okay. So in surface tension, you will learn that pressure inside the water drop is more than the pressure outside. Excess pressure, you will be teaching them, isn't it? Yes. Now, this is an interesting example here. You know that as velocity, so a person is getting down is with a, well, it's not that with a parachute or with a parachute, but the parachute is not shown. So upthrust as well as viscous drag is acting. So now frictional force alone is given, viscous force 400 Newton, 1000 Newton. So this vector is less. So as he falls, you know that the viscous force increases with the velocity, isn't it? This is a formula. So the viscous force increases with the velocity. So as he's falling, the viscous force increases. So at one stage, the viscous force balances the gravity. So he will, at that moment, he falls with a uniform velocity. So he has attained terminal velocity. One more example also you can give. So when raindrop is falling and when you are, when it's falling on you, you don't feel that, see, it is falling from such a great height, isn't it? Raindrops are falling from clouds which are at a kilometer distance, 10 kilometer. So if you feel that only gravity is acting, after traveling through, say, 10,000 meter, 20,000 meter, it should hit you really hard, no? It should really hit you. But you know that raindrops fall on you very softly. Why? It lands on you gently only, no? Is it not? Though it is, unless it is a heavy rain, the raindrops after traveling kilometers of distance, after falling through kilometers of distance, it lands on you very softly. Why?
Ma'am, like we can compare it to a person jumping with a parachute. Maybe initially it will be very fast, but after a while it becomes steady.
Yes, it attains terminal velocity. That's what you're telling, isn't it? It attains terminal velocity. So once the forces on them are balanced, no? So that's the same case here, isn't it? Raindrops, you can consider this as a raindrop and the surrounding as air. It is, see, air is also a fluid. So when you are learning about fluid dynamics, don't think that we are talking only about flow of liquid or flow of water. We are also applying the same principle. Fluid mechanics is also applied to aerodynamics. Okay, so you can consider this as a raindrop and the raindrop falling through viscous air. So same thing happened here. As it falls, its velocity increases, viscous force also increases. This is constant. Buoyancy is constant. At one stage, the raindrop attained terminal velocity. So after attaining terminal velocity, the velocity cannot increase. It will not increase. So it falls on you gently. Unlike in the case of free fall, the velocity increases at what rate? 10 meters per second per second. Okay. Whenever you tell the unit for acceleration, better tell it as 10 meters per second per second. They will understand better. So the change in velocity for every second is 10 meters per second. That's not going to happen when the ball attains terminal velocity. So when you're explaining, no more than the concept, lots of illustration you should give. Lots and lots of illustration. So we are done with the viscosity. So what is that property we are going to learn now?
Surface tension.
Surface tension. So I have shown you some pictures. We have to relate it to surface tension. So can you fill water even after the vessel has become filled? You can try it, no? It is brimming, it is full, and then you can add some more water. So can you see that the water on the surface behave like a stretched membrane? Yes or no? Elastic membrane?
Yes, ma'am. Yes.
So now the surface tension forces can be understood in terms of molecular forces. I think there is a lot of disturbance from my side. I can't avoid it, outside noise. Can you hear me?
Yes, ma'am.
Yes.
Cohesive force. What is cohesive force? The force of attraction between the molecules of same substance is cohesive force. Suppose here, if you consider a glass plate, imagine this is a glass plate, and just pour water. Just pour water. What will happen to the water? Will it stay on the glass plate or it will spread? The water will spread like this, isn't it? Correct? Water on a glass plate will spread, whereas mercury on a glass plate will form a drop like this. Am I correct? Am I audible?
Yes, ma'am.
Am I audible?
Yes. Yes, ma'am.
Yes.
Yes.
Why water spread on glass plate and why mercury is not spreading? This is water. In terms of cohesive and adhesive force, can you tell? See here, the cohesive force between mercury molecule is more than the adhesive force. Adhesive force is force between molecules of different substance. Force between molecules of different substances, adhesive force. Can you see a film? I'm going to break one part here. I'm going to break. Teachers, can you see a film here? Just I'm breaking one part. Just observe. Can you see this thread is curving?
Yes, yes.
It is, when you break, see there is a film. A soap film is formed here. Now I am breaking one part here. I'm breaking this part. Okay. Immediately see with which side it is shifting. Why it's shifting? Still the film is here. Can you see? Can anybody explain why it is happening?
Due to surface tension.
Huh?
Due to surface tension, that layer acts as a stretched membrane.
This side of the. Do you show this experiment to the children? molecules actually attracting the now, if you consider this thread, this thread is held by molecular force of attraction by both the side, molecules of soap on either side. So when I prick one side, there is excess of force on the other side. Okay. So immediately there is unbalanced force.
It's Sum time. How do some insects walk on water?
Can you hear the sound?
They don't walk. They can't walk. Nah. Water has an unusual property. What's that? Each water molecule is attracted by other molecules around it in all directions. But since the molecules at the surface have no molecules above them, they get attracted inward more strongly. These inward forces of attraction create surface tension, thus making the surface act like a stretched membrane. Now, the weight of insects like water strider and fishing spider is very less. So, the force that insects' legs exert on the stretched water surface is lesser than the surface tension. Also, as their legs are spread wide apart, their weight gets further distributed among all the legs. Hence, the insect's legs don't sink and just create dimples on the stretched water membrane, helping it walk on water. Topic.
So now we are ready to understand what is surface tension. So surface tension is due to molecular forces. Okay. So now you know that water spread on glass because water has greater attraction to the glass molecules. Okay, the adhesive force. Adhesive force is force between unlike molecules. The water molecules has attraction. More attraction with glass than with the water. The force between water and water molecule is less. Whereas force between water and glass is more. That's why water spread on the glass surface. Whereas mercury stand as spherical. Mercury will appear as spherical drop on glass. Why? Here there are two forces. That is adhesive force between mercury and glass. Cohesive force between mercury and mercury. Which is more? Which will be more? Which force is more? Cohesive force or adhesive force?
Cohesive force between mercury molecule.
Cohesive force between mercury molecule is more. Okay. So now, if you consider a liquid in a container, water in a container, okay, surface of a liquid. So if you consider, see, the liquid, the molecule here, no, any liquid molecule is acted upon by, there are surrounding molecules. It is surrounded by molecules in all direction, and the force, they experience equal force. This molecule is pulled by this and pulled by this, and pulled by this, pulled by this, pulled by this, pulled by this. So now it experiences equal force of attraction in all direction. So what will be the net force on this? So if this force is balanced by this force exerted by this molecule is balanced by this molecule. So this force is balanced. So net force on this molecule, which is very well inside, is zero. Very well inside is zero. Whereas the molecules on the free surface experience downward force. That's what I explained, you know, that activity was clear. Was it clear? That activity? So I had I made a loop out of metal frame, and then I tied a thread here. I immersed in a soap solution. So a liquid soap film was formed here, and then I pricked one end. Immediately what happened was, you would have noticed that one part became like this. Why? Where there was a soap film. Because there is no soap film this side. So the soap molecules attracted this thread this side. Whereas here there was attraction, equal force of attraction by soap molecules. So this thread was in equilibrium. Did you observe that? Do you want me to do that again? Huh? Please and respond. If you want, I can do it. Do that activity. Okay. So now I'll finish this 5 minutes because I had lots of disturbance. So just I will explain the surface tension. Okay. So that we can understand how the insect crawl and how this concept you can easily make them understand. Okay. Is it okay? Hello?
Yes, ma'am.
Yeah. So now, you know that the surface molecules, the molecules which are at the surface experience net downward force. Net downward force. So now, they are not in equilibrium. So now, if a molecule, so suppose if I want to bring this molecule to the top surface, should I not do work against the, so against the downward force, they are placed on the surface. Okay. So if a molecule from the interior to be brought to the surface of the liquid, we should do work. No, you should do work, isn't it? See, suppose you are taking the ball and then you want to lift it up. Should you not do work? You have to do work against gravity, isn't it? So this work done is stored as potential energy. Am I correct? Similarly, against the downward force, downward force of gravity, this ball is kept here at an elevated position. Similarly, these molecules which are on the surface are existing despite the downward force. So this downward force actually should have pulled it down. No, against the downward force, they are existing. That means they have extra energy. Okay. So now all the molecules on the free surface of the liquid have extra energy, extra potential energy. We call it as potential energy. But you know that every system tend to be in lowest potential energy state or highest energy state. What is the tendency of any system?
Lowest potential.
Lowest. So a free surface will have minimum potential energy. So any free surface tend to attain a minimum surface area. That is why a small spherical drop attain, if you consider a spherical drop here, it attains a liquid drop free from gravity. Suppose a small water droplet on a glass, on a, say, a lotus leaf. On lotus leaf, you can see that it is spherical, isn't it? So why only spherical shape? For a given volume, the surface area of the sphere is the least. It's mathematical concept. If the area is least in a surface, energy is least. Correct? Every free surface, see, you know that surface area should be minimum. Why should be minimum? Because potential energy, then only it will be minimum. Free surface of a liquid tend to attain minimum surface area because of the net downward force. Potential energy is there only for the molecules on the free surface. Every surface of a liquid tend to attain minimum surface area, okay, in order to attain stability. So this property, so the surface tension is the tendency of fluid surface to shrink into minimum surface. So you must have noticed when you fill a glass up to the brim with water, you can still add few more drops. Or have you ever broken a thermometer and observed the mercury droplet will be spherical? So now the free surface of a liquid behave like a stretched membrane. It's like this, a surface tension force because of the cohesive force, the intermolecular force of attraction. It behave as if the surface is stretched. Okay. So when there are no external forces, the shape of a liquid is determined by what? So when there are no external, if you neglect gravity, the surface, the shape of the small droplet is what? Sphere. Why is it sphere? A spherical shape has least surface area, isn't it? That property is only surface tension. So what is the answer for this? The shape of the liquid is determined by what? What answer? Is it determined by viscosity, density, or temperature, or surface tension?
Surface tension.
Surface tension. Insects are able to run on the surface of water. That's what we are going to see now. See, when the insects, so you must have seen, no, some insects crawling on water. So when they are crawling, so when, see here, defying gravity, they are able to float on water. We can't walk on water, whereas insects can walk on water. You must have seen, isn't it? So now, surface tension property is a surface property. The surface tension force act tangential to the surface. So if you consider a layer of molecule of liquid here, they are acted upon by these two forces. The molecules on either side of the line of molecule exert force. So it is as if the free layer is stretched. So when I keep a needle, when I gently float a needle, what happens? The tangential force, no, this force, this tangential force, there is a force in this direction, force, and this can be resolved into two components. This component and vertical component. This horizontal component cancel out, and you know that weight of the needle is acting, and the vertical component of the surface tension will balance the weight. Same thing happen in the case of insect. So now the insect also spread the weight over a larger surface area. So weight available per unit area is less. So now a small depression which is created will make the upper component, vertical component of the surface tension will balance the weight. So they are able to defy gravity. Okay. Water molecules stick together. See, actually it is like the molecules, no, the water molecules here. So when you take, no, this water molecules stick, the molecules are held by cohesive force that they are all sticking. It's like sticking. So now, unless a very large force is applied, unless the insect is very heavy, the stickiness or the surface tension forces will not be altered. So in order to make the water flow, some force greater than the surface tension force should act. Okay. So the weight of the insect is so small that it can manage the weight. It can defy the weight. The component of the force, surface tension force, will balance the weight.